All right, I'm going to do some work here done by gravity, starting with number 21. I'm going to do it in my, I don't know if this, you'd call this pink or purple. It's kind of like a dark pink, I guess. One of my favorites. It's probably getting low on ink, but oh well. Let's see. So 21, I've got a cord is used to vertically lower an initially stationary block of mass m at a constant downward acceleration of g over 4. Okay. When the block has fallen a distance d, so delta y is equal to d. That's also downward because it was initially at rest. The work done by the cords, we want to find the work done on the cord's force, by the cord's force on the block, the work done by the gravitational force, and the kinetic energy of the block, and the speed of the block. Okay, so you could do kinematic stuff with this for sure because we know the acceleration, but we're going to do it with forces and work. So if there's an acceleration of g over 4 here, then I know that that must be, there must be more downward force, right? Because the direction of the acceleration is the same as the direction of the net force. So the force of the cord, I guess that's a tension force, could have called that T, is equal to, I don't know what, or maybe you can figure out just looking at that. But if you were going to make a little, if you feel you have really good intuition about what that's going to be, then you could just fill that in, I think. Otherwise, you could do okay, sum of all forces then is going to be that minus this, and sum of all forces is equal to mass times acceleration. Sorry, it should be a big M to match up with that. And we know what the acceleration is. It's g over 4. So I'm going to have an mg over 4 here and an mg. When I subtract that over and move this here, I'm going to get 3/4 mg. So if you saw that this was a quarter and then you had the 3/4, I don't know, maybe you could spot that. Maybe not, but that's how the work would look to do that. Okay, so for part A now, I'm looking for the work done by the cord's force on the block. So the work done by the cord's force on the block is equal to the force here times the displacement d. And those two things are in opposite directions. So here's the force of the cord, and the displacement is down, so that is going to be negative 3/4 mgd. For B, let's see, the work done by the gravitational force. So the work done by gravity is equal to the gravitational force times the displacement, and those are in the same direction, so that's positive. And part C, the kinetic energy of the block. Well, the total net work that's done is equal to change in kinetic energy. So the net work, that's the sum of these two. So that's, maybe I'll just write a more high-level statement of that. And then adding those two together, I get 1/4 of an mg, or of an mgd rather. That's equal to change in kinetic energy, which is, since it started from 0, the change in kinetic energy is just its final kinetic energy because the initial was 0. So that's 1/2 mv final squared. So I think the answer for part C is this. Is that right? The kinetic energy of the block is this. And last, they want us to say what is the speed of the block. So that's just solving this for VF. So let's see, VF would be equal to, if I multiply both sides by 2, that would give me a 1/2 over here. The m's cancel out, so it looks like it's the square root of GD over 2, I believe. Yep. Here's a fun game to play. Sometimes you get these answers in these problems where we don't have numbers, and you get an expression like this. And if you have if you tend to wonder about things like this, you might just want to be like done with it and be like, okay, great, that's it. But you might wonder, is this dimensionally consistent? In other words, whatever this is, it's in meters per second if we're using SI units. And then this also would have units. So, like, does this expression over here, would the units for this really match up with this? So, sometimes it's a good idea, especially when you don't have numbers that you're working with, just to check that out. I'm not going to write anything out. I'm just going to look at this and think about units. So G would be in meters per second squared. D would be in meters. So G times D would be meters squared over seconds squared. And then I'm taking the square root of that. So sure enough, that's meters per second. Of course, 2 is just a constant, a dimensionless constant. So not a bad idea to check that out from time to time. All right, 22. A cave rescue team lifts an injured spelunker directly upward and out of a sinkhole by means of a motor-driven cable. The lift is performed in 3 stages, each requiring a vertical distance of 10 meters. Here's my little upward displacements. The initially stationary spelunker is accelerated to a speed of 5 meters per second in the first stage, so we're going from 0 to 5 meters per second. And then cruising here, so the forces are balanced, and then back to 0. How much work is done on the 80-kilogram rescue by the force lifting him during each stage? So the force lifting him, that is the upward cable force. So let's see here. Do we know, what is it, 80 kilograms? So let's make a force diagram. So stage 1, call that's this here. Call that 1, 2, 3. I should have called it ABC. That's what they did in the book. Oh well. So this is stage 1. There must be, I'm going to call that a tension force here, which has got to be greater than this because we're accelerating here. How much acceleration is there? Well, I think that's just a real quick kinematics problem, right? I've got a VI, a VF, an A, and I got a VI, a VF, and a delta Y, and I need to know A. So VF squared equals VI squared plus 2A delta Y. So the VF is 5. That's 0. 2 times the acceleration times the delta Y is 10. So it looks like my acceleration is going to be the square root of something. 20, so it's the square root. That's about 1.12, we'll call that. That's what I'm getting there. And that is in the up direction. So if I wanted to write a little net force equation, net force is equal to tension is winning versus the gravitational force. So mass times acceleration is equal to the tension force minus that 80G. So math, I'm getting a tension force here of 874 newtons. Okay, and I think that's what we need to be able to do the part A. Oh, I guess there's not parts in it. How much work is done by the force lifting him during each stage? I don't know why they didn't. Are they going to give the answers? Yeah, I guess we'll just give the answers in A, B, C. So part A, how much work here? So that's going to be the tension force that's doing that work is in the same direction as the displacement, so that is positive work. That's going to be 874 newtons times that displacement. So about 8,740 newtons. Joules, rather, sorry. And then B. I've got there, the forces are balanced, so that means the tension force is going to be equal to that 80G times 10. So that's about 7,840. And in C, I've got, it's going to be, let's see, in C, the tension force is going to back off by the same amount. So if I made another quick force diagram, and here, mass times acceleration would be equal to the gravitational force minus the tension force. So here the tension force is going to be 80G minus the 80 times 1.12. That's about 694 newtons. So that's that. All right. Great. Number 23, sorry. I already did 22. 23. If a constant force of magnitude 80 newtons is applied to, I got a picture here. So let's see. I got a rampy kind of thing, and I've got a force. It looks like it's coming kind of this way, and this angle is 53 degrees, causing the box to move up a frictionless ramp at a constant speed. How much work is done on the box by that force when the box is moved through a vertical distance h of 0.15 meters? And all right, so oops. Hold on a second. Sorry about that. Phone call. Just going to ignore that. So the trick here is, I think you might be wondering, don't I need to know the angle of the ramp so I can figure out this and so on? And the answer is no, you don't, because the work done by that force, which is 82 newtons, and this is going to go up by 0.150 meters. So let's go ahead and just do, if that's the case, the displacement here, let me think about that for 1 sec. Oh, it's going at a constant speed. That's the key here. So if that is true and it's frictionless, I think we can figure out what we need to know. Because, let's see, let's make a force diagram here. We have the force of gravity on this, and since we are at an angle, we could break that up into these components. And then I also have this here. It's my applied force, and that, I think we know that this is 53, but that's not particularly helpful for us here. So I'm going to break that into its components also. Getting a little crowded in there. And it's going up at a constant velocity, so I think what that means to us, what that must mean, here's the normal force. What that must mean for us is that this right here must equal that. Right? Right. So, let's see. Let's say that this is the ramp angle. Let's call that theta. Then this is 3, that's the mass of it, 3g sine theta, right there. And this would be 82 times the sine of, this is 53 and this is theta, so that's 53 minus theta. This is, sometimes when you do these problems, you, and by you I mean me, you get this sneaking feeling that you're not doing it the easiest way that it could be done. So, after setting all this up, I'm going to pause for a second, and we are going to think about what we know so far here, and think about, do we really need to know, do we really need to do all this? This is just making me feel like we're doing too much. So, let's think about what we know here. We know that the net work that's done on something is equal to its change in kinetic energy. Oh yeah, this is much easier than all this. Well, this is a good learning experience for all of us. So the net work here done, what's the change in the kinetic energy of this block? Well, it's going at a constant speed now, isn't it? So this is 0. Okay, what are the forces that are acting on the block? The forces that are acting on the block are, well, there's 3, right? I mean, we made our force diagram, so at least I think the, our efforts here were not totally wasted because we can see those there. Okay, so we have the work done by the normal force and the work done by the gravitational force and the work done by the applied force. And those must all add up to 0. Now the displacement of the block's going up the ramp this way, right? And the normal force is perpendicular to that. So if you think about our definition of work, that work is equal to force times distance times cosine of the angle between them. If this is 90 degrees, then this is 0. So this is, if something's moving this way, then a force acting on it perpendicular, that does not do any work. So this is 0, which means the work done by gravity and the work done by the applied force must be equal to each other, or opposite in sign. So that is all we need to know, because the work done by the gravitational force is equal to negative mg times delta y. And it doesn't matter what the ramp angle is. If we know how much it went up, that is the important thing for work done by gravity. All right, so the work done by gravity is equal to negative 3 times 9.8 times 0.15, which is, I feel like I snatched victory from the jaws of defeat here. Feeling pretty good. I was on the ropes, but we got back up again. Okay, so that's negative 4.4 joules. So that means the work done by the applied force is positive 4.4 joules. So that was way easier than what I descended into there. But hey, that's the nature of the beast. There is often an easier way, and that easier way does not always present itself to one's consciousness immediately. And by one, I mean me. So 24. In figure 732, oh boy, here we go again. We got a psychology book. It's kind of thin. I guess our physics book's kind of thin too, so I shouldn't give the psychology book a hard time. And there's an applied force like that, horizontally, and the book's going to go up. This is kind of feeling like number 23, isn't it? Well, I'm glad we have that experience. I think the magnitude of this force is 20 newtons, looks like. It's applied to a 3 kilogram, it's even the same mass, a 3 kilogram. These guys who wrote this book love to diss the social sciences just for fun. No reference in here. So let's see. The distance here is 0.5 meter, and the angle is 30 degrees. During the displacement, what's the net work done on the book by that force? The gravitational force on the book and the normal force on the book. If the book has 0 kinetic energy at the start of the displacement, what is its speed at the end of the displacement? Okay, so the big difference in these two problems, if we want to kind of lean on our experience here, is that the change in kinetic energy here is not 0. I don't know that it's being pushed up at a constant velocity. In fact, I know it's not. So I think we have enough information this time, though, that we can, I don't know, without even, I don't know if we need a force diagram or not. I think maybe we don't. I'll draw one. I don't know that this is necessary to do the problem. I think you could get away with not having this. So the force of gravity is 3g, and the applied force is 20 newtons, and the normal force is whatever it is, and I think we're going to see in a second. I don't think we need to know. We could figure it out. All right. And I know that this is 30 degrees, this angle. So that means this is 30 degrees, and I know the displacement it's going to go through is in this direction up the ramp. I don't want to draw that in as a line there because that would make it look like it's a force, since this is a force diagram. So if that's 30 degrees, this is also 30 degrees. Okay, so I think we're ready to roll here for our different parts. These are all constant forces, so work is equal to force times displacement. They're not all lined up with each other. The displacement is this way. None of the forces are exactly in that direction, so we're going to need that cosine theta term. So for part A, what's the net work done on the book by each of them? That's all in part A? Okay, so that's confusing. So for the applied force, the work done by that is equal to 20 newtons times the displacement, which is 0.5, times the cosine of the angle between them. The displacement's this way, the force is this way, so that is a 30-degree angle. Quick check, always a good idea, I think, when you're doing, when you're figuring out work. Should this in fact be positive? If I just run that through my calculator, I'm going to get a positive number. Is that correct? Yes, because those are mostly in the same direction. Once you pass the 90-degree mark, that's when you're going to get the negative. So that is correct. So let's see what we got there real quick. 20 times 0.5, pretty sure that's 10. So that's about 8.66 joules. And then the gravitational force, work done by that, is going to be equal to, the force is 3g, the displacement is 0.5. The angle between those is 120. And that is going to give us the negative sign because those are between 90 and 180 degrees apart from each other. So I should get a negative there, and I will, because cosine of 120 is negative. So 3 times 9.8, cosine of 120, that gives me negative 7.35 joules. And then the normal force and the displacement are perpendicular. The angle's 90, so no work there. The work done by the normal force is 0. All right. And I guess I'm looking at I have the answers for the evens here. I'm looking at the way they asked that during the displacement, what is the net work? Okay, so then they wanted the net work. So the correct answer then, the sum of all of the work being done is the sum of these things. So that's going to be, what's that, 1.31 joules? Yeah. And then B, the net work that's done is equal to change in kinetic energy. Sorry, sometimes I write this net work and sometimes I write like the sum of all work, same thing. So that is 1.31 is equal to, if it started from rest, then the change in kinetic energy, if it starts from rest, then that's just 0, so that's 1/2 mv squared. So let's math ourselves into an answer. I'm looking at about 0.93 meters per second. All right, good. No free pizza.